Okay, so welcome to the Flight Test Engineering problem set to work through. The objective of this is to show you how to do the Sawtooth climb data reduction. And we have the problem statement here. The background information was provided to you. And so we're just going to jump right into that. So really what you can do is, using the theory, essentially what we need to do is we need to plot this term, the PIW term, versus the CIW term. And really what's involved in that is we need to know the brake horsepower of the engine, some atmosphere terms, and then some weight terms, a rate of climb, more atmosphere terms, and again a rate of a weight term, a weight ratio. And I think that probably the best way to do this is just to go in and start filling in some data values. So the first one is we've got the PIW term, and PIW we're just going to say is the brake horsepower. So in fact we'll just go look at that. Brake horsepower and times an atmospheric term. There's a sigma, there's another atmospheric term, and a weight ratio. Now you could do it that way, or you can do it the traditional method, which is you just go through here and you have each line corresponding to a separate data value or some value that you've calculated. And so that's what we're going to do here. You could do it just by plugging in everything, but this is more of the traditional way, and it's essentially what you have is you have a line number over here. So column A is a line number. So when we're saying, for instance here, 5 plus 460, really we mean line 5, which is outside air temperature, plus 460. And what that's really doing is just getting us to a Rankine. So we'll just do that over here. So that is 5 plus 460, 517. What is the standard temperature at 2,000 feet? So here's the height above sea level that we are. Well, what is that standard temperature? Well, you could either go look it up in the back of some aerodynamics book, or you can, let's see, here's another source for it. 2,000 feet, the atmospheric pressure ratio is 0.929. The temperature is 511 Rankine. So we can just go ahead and plug 511 Rankine. Unfortunately, notice that should have been in Fahrenheit, shouldn't it? So let's go fix that. 51.8 Fahrenheit is the standard day temperature at 2,000 feet. Let's go back to our Excel spreadsheet, remembering the value, and just go plug that in. Okay, so to get to Rankine, we would have line 7, which is that one. So 7 plus 460. It's actually 459.67, but that's close enough. Outside air temperature, and I have doubled up on that one, so line 9 is the same as line 5. And now we need to get that to Rankine, so that's line 9 plus 460. And then we're going to get some temperature ratios. So that's line 6 divided by line 8. Line 6 is the outside air temperature in Rankine. Line 8 is the standard temperature in Rankine. So we can do that pretty quickly. So 6 divided by 8. Okay, so it's a little bit warmer than normal. And then the inverse of that, of 8 divided by 6, we could either calculate it or just do that inverted. 2.99. Okay, we're given these values. What about this value? Well, we have 2,700 RPM at 27 inches of mercury for the manifold pressure at 2,000 feet. What is our horsepower? Well, that's where we've got to go look at an engine chart. engine curve. And it gives you an example calculation. And it says over here how you do it. And you basically have to find points A and B and C and D and whatnot. And so the first step is locate on a full throttle altitude curve for a given RPM and manifold pressure. So locate A. So we had 2,700 RPM and 27 inches of mercury. So there's 28 and there's 26. So we're right about here. Okay? And then it says locate B. B is over here on this level C, or sea level performance. Look at B on sea level curve for RPM and manifold pressure and transfer to C. C is along this area, so we need to go find 2,700 RPM and 27 inches of mercury. That would be this location. And then it says transfer over, which just means that we carefully transfer that over there. Okay. And now what? Connect A and C. There's A and C, so we can connect those two. A and C. Alright. A straight line and read the horsepower to give an altitude D. Well, standard altitude, we've got pressure altitude right here, 2,000 feet, which is what we're at. We go up, and essentially it's right there, and then read over. That's 170 horsepower. So the answer for that is it's 170 horsepower. That is where we plug in this value, 170. Now, you have to be careful, and you notice in the notes I was not completely consistent with that, because it says over here to modify the horsepower for a variation in air temperature from the square root of the temperature ratios. So if you do step 4 here before you transfer it over to the Excel sheet, then you can't do it again in step 16, which is what I did on one of the examples. So really what we should have here would be the horsepower, which is line 15, times the square root of number 12. And that just says that if you have a hotter than normal day, you have a little bit lower density for that same pressure, which means that you have a little bit less oxygen content, which is less performance of the engine. Okay, and then we have number 2 times 11, the rate of climb times 11. Okay, rate of climb times 11. Delta is the temperature ratio. Okay, that's not right. Delta is the pressure ratio. Delta. So we need to know what the ratio of pressures are at 2,000 feet. And again, we can go to either our textbook in the back of an aerodynamics book, or you can just go look it up. So at 2,000 feet, the pressure ratio is 92/98. Just copy that in. Okay. Now at this point, you're going to be tempted to go over to this equation here and just take in the density ratio, and you should not do that because the pressure is not standard. So we can actually calculate that. Right, if we know that pressure is equal to density times R times T, then just doing a ratio would say that delta is equal to sigma times theta. Okay, so if we know what sigma is, it would just be delta over theta. That's just delta over theta, which is the temperature ratio. There. 9205. Okay, so the square root of that there, the ratio of the weights to the standard weight. Well, we were operating at 2,506 pounds, but the aircraft is actually we're testing at 2650, which is for that 172 the gross weight. So we were at 94% of gross weight. Square root of 19 is, well, calculate that. It's just the square root of that weight ratio. Okay? And then the weight ratio to the 1.5 power would be weight ratio to the 1.5 power, 0.91. So PIW, if we remember back from our PIW is brake horsepower, some temperature and density ratios, and then the square root, or the 3/2 power of the weight ratio. So if we go look at that, we have, make sure we did this right. PIW is brake horsepower, which is C17. We pre-multiplied it by the square root of the temperature. And we've got that temperature ratio. And then density ratio. And then we're multiplying it by the density, which is C21. And dividing by C24. Okay? Okay. And just to be very clear here, when we have this is the square root of theta. That is what we have, because here we have the square root of C13, which is this line 12, and that's 8/6, which is standard over outside air temperature. So we have in fact done PIW correctly. And then CIW is H dot, let's put this a little bit there. Come on. So CIW is H dot, and H dot times, there's the temperature ratio, so that's what this term is, times C21, which is square root of sigma, which is there, and then dividing by the square root of the weight ratio. So there's the square root of the weight ratio, and we're dividing by it. Okay, so PIW and CIW are correct here. So you should end up for this first one at 2,000 feet with an outside air temperature of 57 Fahrenheit. You had a rate of climb of 666 feet per minute and a weight of 2506. You should end up with a PIW of 176 and a CIW of 663. Now what you can do is do that same process for all of the lines, all the columns, and you would end up here. Now the thing is that we really want to have a curve that describes that CIW PIW. So if we plot those data points, this is what they look like, and then we kind of want to have a line between them, make it a linear function. So we can do that pretty quickly with just finding the slope. So if you take the slope command in Excel, you can find the slope of CIW versus PIW, and that value in fact is 4.16. And then you can look up the intercept as just the intercept of CIW and PIW, and that tells you where it's going to intercept if you went to a PIW of 0. So in other words, that defines the curve, the line. And then when you do all of your rate of climb, then you can just go plug those values in and do your renormalization to a standard rate of climb, a standard climb performance. Okay, so with that I will sign off here and let you guys try it some more.